Swayam Prabha. Digital India. Educated India.
Welcome to this session on laser beam welding process under the course Advanced Manufacturing Processes. In the last few sessions, we have discussed about the solid state welding processes, then the electron beam welding process and plasma arc welding process. We have also seen the working principles, process requirements, advantages, limitations and applications of these processes. Moving on, let us see another advanced welding process, namely the laser beam welding process. We have already discussed about the laser beam machining process in the module 3. So, this laser beam welding process is also similar to that process in the sense that the same kind of laser will be used, and here instead of cutting or removing material, we will confine the laser beam power into just melting the materials and fusing the two materials. In the previous lecture, we have discussed about the principles of laser formation, then some unique characteristics of lasers and their applications. However, in this session, we will confine our discussion to the welding aspects along with a brief description of the basics and features of and applications of laser beam welding process. The process principles, advantages, limitations and applications of some other important welding processes like forge welding and diffusion welding will also be covered in this session. Now, let us move on to first the laser beam welding process. As we have indicated already, so this is also a thermal based process in which heat will be generated by the application of laser beam. The coalescence of the surfaces of the material will be produced by heating the workpiece due to the impingement of the concentrated beam, laser beam, which will be coming out from the laser generating device or we call as laser source. Let us refresh ourselves with the laser system. Although we have already discussed, quickly let us have a recap of the process what we have discussed already. It is a device that produces a concentrated coherent light beam of single frequency by stimulated electronic or molecular transitions to lower energy levels. Laser is an acronym for light amplification by stimulated emission of radiation. If we recall our earlier discussions, we can see that this is in for producing laser, one material which is called say lasent this latent material has to be excited, or in other words the electrons in the orbits of low energy. So, here energy is E1 and here energy is E2, which is higher than E1. Similarly, if we go on to the other orbits, so energy level will be higher subsequently. Therefore, if we apply some or if we supply some energy, this is additional energy to the low energy electrons. So, these are nothing but electrons with different energy levels as we have indicated. Now, if these electrons at relatively lower energy level is shifted to or knocked up to another level which is at higher energy, and this is shifted to another level which has got further energy, then they will come to an excited status or excited state, which is very unstable for them to remain for a longer period. Therefore, these electrons will always try to jump to the next lower energy level. They will always keep on trying this. In turn, again they will try to come to their original energy level. While doing so, at this moment when it was here, say they were at this E3 level. Now, while coming back to E2 level, where E2 is less than E3, the difference in the energy del E is nothing but E3 minus E2. This energy or delta E is equivalent to h nu, and this is nothing but the energy, and this energy will be emitted in the form of some packets, or also called as quanta, or these are in very simple meaning, it can be known as packets of energy. These quantas are also called photons. So, they have single wavelength and therefore, they are, you can say, monochromatic in nature, and these quantas are nothing but what we call as laser. Therefore, while coming back here, so they will emit some radiation, this is nothing but h nu. Similarly, while coming out from here, they will emit some radiation, this is nothing but h nu, which will be now equivalent to E2 minus E1, again it will be delta E. So, this is nothing but what we call as laser, here. So, this is the basic principle how we produce or we can get laser from a lasing material or a lasent, that is lasent. So, for this we need an external source of energy that we call as additional source, or this we call as excitation energy, which will be generally in the form of some additional UV light or some other arrangement, and the material in the excited state will emit this laser energy or the photons. These will be allowed to get reflected several times inside the device or inside the lasing device, and after it gets amplified to a certain level, then they will be allowed to come out from the device or the lasing environment, from the system through special mechanisms, and that will be taken away or collected for different applications. So, this is the basic principle of laser production that we will see how they are being manipulated further for different applications. In the laser beam welding process, the laser beam is directed by flat optical elements such as mirrors and then focused to a small spot for high power density. At the workpiece where we want to do the welding operation using either reflective elements or some special lenses. This is the schematic of the laser system. This is what just we were discussing just now. It is schematic is on the screen. This is the lasing material I was talking about, or also called as lasent. So, here it is shown as a rod which can be say ruby rod if it is a solid state material, or neodymium, yttrium, aluminum, garnet rod. So, these are some of the lasing material or lasent, solid state lasent. Apart from that, we can use some gases also like argon system, helium argon system, or carbon dioxide is a very popular lasing material. Now, this lasent is being excited by some additional energy. So, this is the energy supply system, additional energy supply system. Generally, these are like krypton or xenon flash lamps. So, they pump energy in the form of some light waves, which will be responsible for causing the population inversion. What is the situation called population inversion? Like just we have discussed just now, the electrons from lower energy level to higher energy level will be knocked up. That means that will create a very unusual situation of electron densities at the cells, outer cells, where generally the number of electrons will be different from that of inner cells, or for that matter we can say each cell has got some fixed number of electrons because owing to its electronic configuration. Now, if we disturb that number which is naturally occurring, say for example, in the outer cell if there were 4 electrons, now if we knocked up few more electrons onto the outer cell, say for example, it has come to 8, then it is called a situation that is population inversion. We have created an abnormal situation of different abnormal population in the outer cell. Now, at this stage, as I have already told, the electrons are in an unstable condition and they will always try to jump to the nearer cells or low orbits. to come to, in order to come to their normal conditions. Therefore, they will always try to jump down to the next orbits, next lower energy level orbits, and thereby making the population inversion condition going back to the original condition. However, because of this additional source, this population inversion will be kept on creating or will be maintained over a period, and therefore, these electrons, although they will jump back to the next electron energy, next lower energy level cells, some more electrons will be again brought back to or knocked up to the other higher energy level cells. However, this while jumping down to the smaller energy level cells, the energy released will be in the form of some photons, or we can say in the form of some radiations, which will be, as shown in the figure, will be continuously being reflected in this system. This is shown as 100% reflector system. So, in between the chamber or the enclosure, so some specially placed mirrors are there, which will be responsible for their continuous reflection of these beams, and after getting amplified to a certain required level, they will be allowed to come out through this lens or the mirror, through this mirror system, which is partially reflective. That means, some portion of the amplified energy or the beam in the form of laser will be allowed to come out from this system, and this amplified energy, which is called laser, will be used for industrial purposes or for other purposes, which can be for say medical purposes as well. It is as we have already seen the schematic or the principle, this laser welding device is a non-contact device in which there is no conventional electrode and a workpiece contact or the tool workpiece contact situation, and therefore, there is no question of applying any pressure as well. Inert gas shielding is generally employed to prevent oxidation of the molten poodle, and filler metals may be occasionally used. As we have already spoken about, this is a thermal based process and causes material to get melted. Therefore, it is prone to oxidation if the environment is not controlled properly. Therefore, some shielding gases for certain materials which are very easily oxidizable, very susceptible to oxidation, should be used. Some shielding gases should be used for protecting the weld pool from this oxidizing agents. Now, let us talk about the gas lasers, which is generally widely used in case of laser beam welding, and as we have already indicated, the carbon dioxide is the most popular gas laser. The electric discharge style of carbon dioxide gas lasers are the most efficient type currently available for high power laser beam material processing. These lasers employ gas mixers primarily containing nitrogen and helium along with a small percentage of carbon dioxide. An electric glow discharge is used to pump this laser medium, that is to excite the carbon dioxide molecules. Gas heating produced in this fashion is controlled by continuously flowing the gas mixer through the optical cavity. Thus, carbon dioxide lasers are usually categorized according to the type of gas flow system which they employ. These are namely the slow axial flow gas lasers, fast axial flow gas lasers and transverse flow gas lasers. Let us see the slow axial gas flow lasers. They are the simplest of the carbon dioxide gas laser family. So, gas flow is maintained in the same direction in this case as the laser regenerator's optical axis and the electric excitation field or the gas discharge path in the same direction. These are capable of generating laser beams with a continuous power rating of approximately 800 watts for every meter of discharge length. A folded tube configuration is used for achieving output power levels of 50 to 100 watts maximum. And in case of fast axial flow FAF in short gas lasers, they have a similar arrangement of components as that of the slow axial flow gas lasers, except that in the case of fast axial flow gas lasers, a root blower or turbo pump is used to circulate the gas at high speed through the discharge region and corresponding heat exchangers. Fast axial flow gas lasers with continuous output power between 500 to 6000 watts are easily available. Then comes the transverse flow gas lasers. These lasers operate by continuously circulating gas across the regenerator cavity by means of a high speed fan type blower. While maintaining an electric discharge perpendicular to both the gas flow direction and the laser beam's optical axis. Transverse flow lasers with continuous wave output power levels between 1 and 25 kilowatt are easily available. A schematic of this type of flow gas laser is shown here in the screen. So, here this is the mechanism. So, all the requirements or the components like polarizing mirror, rear mirror, all these components are integrated in this system, and this is where this is the device through which we can have the beam output. This gas flow direction etc., are also being shown in this figure. Now, let us look at the advantages, major advantages of laser beam welding process. So, this includes the following. Number 1, heat input is close to the minimum required to fuse the weld metal. Thus, heat affected zones are reduced and workpiece distortions are minimized, as we have already spoken about. So, this is also another thermal based process and heat affected zones is most likely. However, because of the characteristics of laser that it can be just focused to a very narrow zone, therefore, the heating effect to the nearby material of the weld point will be much less. This is clearly an advantage of this process, like we have seen in the electron beam welding process also. In that case also, the beam can be concentrated to a very small diameter spot, and therefore, the heat affected zone nearby to this working zone will be much less. Number 2, no electrodes are required in this case. Welding is performed with freedom from electrode contamination, indentation or damage from the high resistance welding currents. In fact, there is no current being applied to the workpiece or the system. In that system, only the laser production system does need the power supply, that is different. Laser beam welding being a non-contact process, distortions are minimized and tool wears are eliminated. Welding in areas that are not easily accessible with other means of welding can be done by laser beam welding, since the beams can be focused, aligned and directed by optical elements on a very precise area. This we have spoken about in case of electron beam welding as well. So, even if there is a small constriction, so this laser beam being very thin in diameter or the diameter of the beam is very less, can be guided to a very restricted area as well and welding can be done, in which case perhaps the conventional welding electrodes could not be inserted to reach that particular area. And of course, the conventional welding rods will give a macro level welding spot, which can be reduced to a very narrow or small zone in case of laser welding. Therefore, it is suited mostly for micro joining or micro manufacturing applications. Laser beam can be focused on a very small area, permitting the joining of the small and closely spaced components with tiny wells. That is usually, ideally it is suited for most of the micro fabrication purposes. Then wide variety of materials including various combinations can be welded by laser beam welding method. Thin welds done by laser welding or small diameter wears are less susceptible to burn back effects. This is clearly an advantage. The burn back is quite often noticed in arc welding for small and thin sections, which can be easily avoided in case of laser welding system. Metals with dissimilar physical properties such as electric resistance can also be welded very effectively here, because electrical resistance does not come into the picture in case of laser beam welding process. And no vacuum or X-ray sealing is required in this case, which is clearly an advantageous situation. Laser welds are not influenced by magnetic fields, as in the case of arc and electron beam welds, where magnetic field influences the beam itself and it can deflect the beam from the actual point of focus, etc. But here in this case it is not so. They also tend to follow weld joints through the root of the workpiece, even when the beam and the joint are not perfectly aligned. Then the aspect ratios, which is nothing but depth to width ratio of the order of 10:1 could be attainable in this laser beam welding process. This process can be automated very easily and controlled by robots also. The process gives very high repeatability, which is very important as far as the process performance is concerned. It provides very high accuracy, it provides very high control, accuracy of control is very high and high speed can be obtained. Let us at the same time note few limitations of this process as well. The joints that are obtained by laser beam welding must be accurately positioned laterally under the beam and at a controlled position with respect to the beam focal point. This is very critical for accuracy of the welding process. In case of mechanical clamping of the weld joints, it must be ensured that final position of the joint is accurately aligned with the beam impingement point. The maximum joint thickness that can be welded by laser beam is somewhat limited. The weld penetrations of larger than 19 millimeter are difficult to weld. High reflectivity and high thermal conductivity of materials like aluminum and copper can affect the weldability of lasers. This we have of course, we have seen in case of laser beam machining as well, where it is difficult to machine those materials which has got very high reflectivity, particularly that of like copper and aluminum and their alloys. These materials have got very high reflectivity, and laser as such does not work very well with this type of materials. An appropriate plasma control device must be employed to ensure the weld reproducibility while performing moderate to high power laser welding. Lasers tend to have a fairly low energy conversion efficiency, which is generally less than 10%. So, this is a point of concern as far as the economics of the system is concerned or economics of the process is concerned. Some weld porosity and brittleness can be expected as a consequence of the rapid solidification characteristics of the laser beam welding. The rays of laser are harmful to human body and needs precautions. Now, let us see few applications of this process. It is being used in the following sectors, like in defense applications, aerospace applications, automotive applications, marine applications, medical applications, building constructions, electronics, power generation and networks, alternative energy devices like fuel cells, solar power and wind turbines, nuclear applications, oil and gas industries, and then many home appliances. Now, let us move to few new trends in laser welding, which is transmission or overlap welding. Joining of polymers by lasers is a relatively new area which is achieved using a laser transparent material and laser absorbing material. The schematic is shown in the screen here. So, here as shown in the screen, there are two materials. The upper material, this is transparent to laser. So, laser can penetrate this material and fall on the other material, and this material, the bottom material, is laser absorbing material. Therefore, the material here gets heated up upon this incident of this laser material, and therefore, this heated material then gets fused to or gets bonded to the top material because of the application of the light pressure on them, and this molten material can get both the halves bonded. So, this is called laser overlap welding process. The laser beam penetrates in this case the upper material and is absorbed by the lower material, thus heating up the lower layer directly, that we have seen in the screen in the figure. This layer transports the heat indirectly via heat expansion and conduction to the upper layer, so that both materials are simultaneously heated up and melted. External pressure can be applied to make them get intimated, which can give higher strength to the welded materials, which is almost equal to that of the base material. The benefits of such a transmission welding process through laser is that the weld is inside the component. This is very important, that is not exposed to the environment or outside we can see anything. The surface is not affected and no microparticles are generated in the joint. The laser beam is absorbed by the lower component and local heating does take place. Due to conduction of heat, the upper component is melted. Through the application of external pressure, solidification of the melt zone occurs, yielding a joint. In brief, in this laser welding process, we have studied the process and the features of the laser beam welding, laser applications and new trends in this category. Let us discuss some other welding processes. First of all, the forge welding process. It is one of the oldest known processes to the mankind. In this process, the ends of the parts to be joined are heated to a temperature slightly below the solidus temperature and a pressure is applied, so that a fusion joint is obtained. The process is similar to the traditional method used by blacksmiths. The force can be applied by manual blows, continuously or repeatedly by a machine or by rolls. In case of ferrous alloys, a thin layer of iron oxide gets formed when the heated metal is exposed to atmospheric oxygen. This oxide layer has to be removed before further weld passes. Flux is applied to that, so that the oxide layer becomes more fluid and under pressure flows out to the joint. Borax and silica sands are used as fluxes. Wrought iron and low carbon steels can be easily forge welded. It is a slow process and is a more labor intensive process. The quality of this weld depends more on the skill of the welder rather than the process. Hence, this is an expensive process and not much in use in industries. Another process is diffusion welding process. Diffusion welding process is also known as diffusion bonding process. The diffusion can be achieved when one keeps two pieces in intimate contact under pressure. The pressure used in the range of 35 to 70 megapascal. By using heat, the bonding time can be further reduced as the diffusion process gets accelerated through heat. The heat applied is much lower than the melting points of metals. The pressure needs to be kept optimum such that there is no plastic deformation. A complete intimate contact is essential in this process. A filler material can be used and is kept between the two metals to be joined. It aids in the reduction of operating temperature and permits some atmosphere around the joint instead of using a vacuum. In one method, the plates are kept together in contact inside the chamber and the plates are heated through normal electric resistance. During heating, an inert gas is pumped inside the chamber to provide uniform pressure on the process to be joined. This method is used for joining non-ferrous metals since the pressure and temperature are relatively low. In the second method, vacuum chamber is used and plates are kept under contact inside it. Force is applied mechanically by means of dead weight or a press. As the pressure applied can be higher, it is suitable for welding ferrous metals. The filler material, if used, its thickness is in the range of 5 to 25 microns only. In such a case, it is expected that the temperature required for bonding is reduced by the formation of a eutactic alloy. Thus, the filler metal diffuses into the two metal plates and forms a eutactic joint. Diffusion welding can be used for joining metals to metals and metal to non-metals as well. Since diffusion welding method is used in joint formation, metallurgically the joints are sound without any defects. It produces neat welds requiring no further processing on it, unlike many other processes. Now, let us summarize what we have studied in this session. We have discussed about the laser beam welding process first, then briefly we have refreshed how the laser is being produced and different requirements, applications and limitations of the laser beam welding process. We have also discussed the forge welding process and diffusion welding process. The potential applications of these processes have also been discussed. We hope this session was informative and interesting. Thank you.